دقايق أسئلة إن شاء الله.
Bismillah ar-Rahman ar-Rahim. Good morning, everybody. I thank you to be all here. What I'm going to talk about today is very soft and easy. Oliver said it is very difficult to do simulation of X-rays. Mario said it is impossible to do dynamics unless you are very rich guy. I will say it's very easy to do electronic structure calculation and get results that help really understanding real chemical problems. So I am an easy man. So don't worry now what we will talk about. We will talk about three parts in this presentation. The first one about structure and dynamics of molecules. I will take a specific example of a biomolecule, a medicine, which we treated and reached results which helped really the mankind. Second part, we will talk about strange type of hydrogen bonding called unconventional hydrogen bonding. And third part, because of the 2 days, everybody is talking about business and projects that have real applications. I will talk about renewable energy, specifically Dyson-sized solar cell. Our future perspective is in this field on the hydrogen storage and design of porous materials. Now, electronic structure, we will look at this drug receptor interaction, and this is a field which is very important in drug design. And there is something called biochemical conformation. The action of drug depends to great extent on this, what they call it, biochemical conformation. So the first thing is when you treat. Now, molecular geometry is very important, bioactive conformation. We will talk about this disease, the Parkinson disease. This is a neuroaggressive disease, results from the loss or decrease of dopamine level in the brain. So we can take dopamine. No, dopamine cannot cross the blood-brain barrier. But what can cross the blood-brain barrier is this compound. This compound is called levodopa. Levodopa, this one, can cross the blood-brain barrier and get decarboxylated inside the brain into dopamine, and the problem can be solved. The problem starts when we know that this is an oral administration. Oral administration means going to stomach where a lot of acid, and decarboxylation takes place directly before it reaches the brain. So what they do, they give the patient a lot of levodopa, a really large dose. But a large dose means a large amount of dopamine in his system, and this means a lot of side effects which you don't need to know. This is exactly like the side effects of chemotherapy. What they came with a sacrifice. This is the sacrifice. Another compound, which both are amino acids, is called carbodopa. Carbodopa can be a little bit more easier to be carboxylated than levodopa, so it will be decarboxylated instead of levodopa, and leave a reasonable amount of levodopa crosses the blood-brain barrier. This is what happens. So the drug is composed of a mixture of both carbodopa and levodopa, and both are administered. Carbodopa just to satisfy this. What is our goal? This is our aim. Now, as a theoretician, we want to know what exactly happens, what's the mechanism of decarboxylation, why carbodopa interact that strongly with the enzyme decarboxylase, DDC enzyme, which is responsible for decarboxylase. It binds the enzyme and keep it away from levodopa. This is our work. And these three questions which we answer. The first step is to get the biochemical conformation of both. And that's what we did. Levodopa was very easy. And we simple optimization, we arrived at a structure which the potential energy surface is really deep, parabola, and deep, clear, global minima is clear. If you notice here, the orientation of the carboxylic group and the amino group are away from each other, and this suggests that the fetal ionic structure is not easy, and this is rare one, because the fetal ionic structure is some 70 kilocalorie above the ground distance. Now, what about carbodopa? Carbodopa situation is completely different. The potential energy surface is complex and rough. Actually, it is flat with many local minima near to each other. We can locate these three structures within 3 kilocalorie per mole energy difference between them. So we didn't decide which one is the global minimum structure to start with. We did molecular dynamics here. We did the molecular dynamics to refine our results, and we came with this structure. This structure came with dynamics. It took about 1 picosecond dynamics. We examined 35,000 structures, all in the vicinity of the minimum. We don't go away, but we explored the minimum energy level, and this is the overlay of 1,000 structures, and shows that the vibrations are here in critical in this region. There's a lot of deformation occurs here in this compound. Okay, now we have the structures. We go to the next step. What is the next step? You are going to the stomach. The drug is going to the stomach. Stomach, a lot of acid. Protonation will take place. Again, levodopa is a straightforward protonation. Protonation took place to the most negative centers, and these are the proton affinities computed for this one. For carbodopa, the situation is completely different. And this is a movie like the movie Mario showed, but it will end up with completely different result. Let us see what happened. Now, a proton approaches carbodopa, and it grabs the OH of the carboxyl group and takes it away as water molecule. It takes a water molecule away, leaving the molecule like this one. So there is no carboxylic group. What we have a carbonyl group and a hydrazine. So this is carbonyl hydrazine compound. Completely different. In the stomach, once the drug came in the stomach, levodopa still an amino acid with the carboxylic group and the amino group protonated, but in the carbodopa it's become like this. The carbonyl group is adjacent to the amino group. This is the reason why this is active in binding the active sites of the DDC enzyme and leave levodopa to escape and crosses the blood-brain barrier. Now, energetics, and this is easy computed. We have made some conclusions about what we have here. Carbodopa is more basic and more acidic and can grab protons easier and all this stuff. Decarboxylation process, we examined the two routes. One route, we call it dry route, no assistance from the solvent, and this is a converted bus where a proton transfers from the carboxyl group to the amino group, forming some sort of splitter ionic structure, This is simultaneously followed by breaking of this bond. So this is a conservative reaction where a proton transfer and the cleavage of the CC bond. This route involves a barrier of about 75 kilocalorie per mole. The other route depends on water. Water gets in and forming this bitter ionic, so this bitter ionic form. With this bitter ionic form led to this transition state, which followed by breaking of this bond, forming the dopamine and water. This route is energy barrier is much lower than the first route. So this water assisted decarboxylation in this case. This is some energy quantities related to the reaction and transition states. These are the methods examined for the process. And of course, each time you have to choose and validate your theoretical model. And now we can go to the second part of our talk about the unconventional H-bonds. Covalent and non-covalent. Non-covalent interactions are very important in chemistry and in biology. Specifically, hydrogen bonds. We all know hydrogen bonds. Bonds formed between hydrogen, between two centers, two more electronegative centers, nitrogen, oxygen, and fluorine in many cases. Something like this. This is the traditional form of hydrogen bond we know, while X and Y are two electronegative atoms. The nature of the hydrogen bond is well stated and described something like 80 years ago by Paul in his very famous book, Nature of the Chemical Bond. We have it here and all we studied it. He says that it will be found that the significance of the hydrogen bond for physiology is greater than that of any other single structural feature. Okay, we know that and believe these words. But we are not talking about these conventional hydrogen bonds. We are talking about something else, called unconventional hydrogen bonds, ionic hydrogen bonds. Ionic hydrogen bonds these can be formed. We are interested in ionic hydrogen bond involving carbon. Carbon-based ionic hydrogen bonds. Carbon-based ionic hydrogen bonds is formed when an ionized hydrocarbon containing CH2 interact with solvents containing electronegative atom. So when you have ionized hydrocarbon as a proton donor and some oxygen or nitrogen lone pairs as electron acceptor, and also in some cases when you have bi-electron pairs. This is the hydrogen bond we are talking about. Hydrogen bond between ionized charged hydrocarbon containing CH, and this is the ionized thing, and oxygen and nitrogen or bi-cloud here. This is the unconventional thing. This comes from when you have ionized protonated benzene or cyclopropane or any kind of heterocyclic compound like the one we were talking about. This kind of hydrogen bond is stronger than the conventional hydrogen bonds. It may reach 35 kilocalorie per mole strength, and it is critical in many fields, especially in biology, but even in chemistry, ionic cluster, radiation chemistry, and ion cell observation is areas depends on this kind of hydrogen bonds. Why we went to this area? Because theory here is very weak when we are talking about non-covalent bonds. You have to be critical for the choice of your model. Why we went there? Because of this experiment. This experiment was being the hydration of pyrimidine, radical cation, and its stepwise solvation. This was carried out by Dr. Sam's child group in the United States in Virginia, and they had a very complex experiment the ion mobility drift mass spectrophotometry experiment. During this mass, they got this one. This is the mass spectrum they got. This is the pyrimidine, and when they get it ionized in water, what they did actually, they injected pyrimidine radical cation with helium and water under pressure and different temperatures. They get species, up to 9 species here. The species they didn't identify, but they experimentally, it is very difficult sometimes to recognize this. They found the pyrimidine radical cation with water, forming water, 1 to 5 solvation, and water clusters of 4 to 9 water molecules are also formed. How this forms, what type of energy we are talking about here, what type of bonding in this system, this is the question he wanted us to answer. And that's what we did. First of all, we made a survey of the theoretical methods available to choose the method. The choice of the method was very critical because the energy we are talking about is very small and a lot of correlation there. So we made a benchmark calculation at a high correlation level and make it for small molecules and make it a reference. And we tried several different DFT and NB2 calculations. We arrived finally at this level of theory to satisfy the requirement of accuracy and reproducibility of that. We used DFT M06-2X with this basis set to describe the system. The system of pyrimidine radical cation and protonated pyrimidine with water has been calculated, and we arrived to something like that. With one water molecule, of course, we corrected the energy difference for subtraction, for 0-point energy, and for basis set superposition error. This is an example of one water molecule, and this is 2 water molecules with pyrimidine. And this is 3 water molecules. As you see here, the chain starts to form. The change, with this type of change, the binding of energy a bit smaller and the length taller until the force. After the force, this type of chain stops. And this coincides exactly with the mass spectrum he did. We repeated this experiment not only with water, we repeated with other solvents, and we repeat the calculation for methyl cyanide and methanol. And this again, ionic hydrogen bonds is formed, and the strength is calculated as the binding energy corrected for this system. And this paper opened a lot of work they did after that in Denmark. They have a lot of conclusions, but we are not going into details of the results. But we have good results here. We have dissociative proton transfer reactions. We computed delta H for all these reactions and thermodynamic properties also. Now the third part is the renewable energy sources. I said it is we need sometimes to go to the market and find funding for projects. And if you're gonna do this, you want something sound. Hydrogen bonding will not get a lot of money for projects, but renewable resources will have. We did some calculation about the dye-sensitized solar cells, where an organic dye is sensitized. I will not go, everybody knows that the solar energy is the future. There is a lot, the solar energy falls on the earth is 4 times magnitude than the energy we consume in the whole year. So we have a lot of energy God sent it to us, and we need to use it. The problem is how to implement it and how to use it. This is the idea of the Dyson style solar cell. It is a competition between two reactions. The first reaction is injection. Injection involves excitation of the dye. This is the first excited state. It goes from the ground state to the first excited state. If we are lucky enough, the LOMO is close to the energy of the conduction band, so injection into the conduction band of a semiconductor takes place, and the electron escapes into the external circuit and goes like this. If you do this, you have electricity. It goes to the electrolyte and then back to the guard. You have now a closed circuit. This is the first bus. If this is the only bus, then you will have a high efficiency of the Dyson style cell. But there is a competing reaction. Competing reaction where the excited electron return back to the ground state and no electricity, or it goes to the conduction band, but from there it returns back to the ground state, and then you don't have any electricity. So you want to adjust the condition to make the first reaction is the more efficient. This is the time scale we are talking about. We want in colors, we want the green to be superior over the red. The red pass is the deactivation here, or is the recombination in any way. But this is the only way, the green one is the only way which we need to have. Organic chemistry is fascinating in one thing, is that you can play a little bit, and they are very clever in preparing organic compounds. So this kind of dyes, which we call it donor bi-bridge acceptor. Donor bi-bridge acceptor. This is a donor, and this is a bi-bridge, and this is the acceptor. The acceptor ends with an anchoring group, a group that can catch the titanium oxide surface. If this happens, then you will have a transfer, electron transfer from the donor through the bi-bridge into the titanium oxide. If you do this and you can get a good dye, you will have this reaction going in the right way you want. We tried several dyes. This is some biline squalene as photosynthesizer. We use it, and this is the first time we used. And we also have made the choice of the theoretical model, which DFT method is suitable for such kind of calculations. We end up with, I think PBE methods are the best, and we start calculation like this. This is another approach we did. We did several papers on trying to find the effect of substitution to increase. This is the donor, triphenylamine donor, this from donor, and this is the bi-bridge, vinyl vinylene moiety as a bridge, and then the cyanocarboxyl group. This is the anchoring and acceptor. So electrons will go in this way. We want to substitute here to increase the withdrawing power of this dye. And that's what we did. And we examined the dipole moment and charge transfer, and this is the relief map, three-dimensional map for the electron density to see how the electron transfer is taking place. All these studies will just examine how the electron cloud moves with the transfer. As you see, these are the natural transition orbits. This is not the HOMO and LOMO, these are natural transition orbits. In the natural transition origin in the ground state, all localized on the dome moiety. After transition, everybody, all charge density is on acceptable mode. Okay. So we have real charge transfer, and here, this is the energy difference, the energy gap between the HOMO and LOMO, and this is the conduction bands of the titanium oxide, the semiconductor. What we can do, this as a model, this substitution model, we make another substitution model to get into the infrared. We can calculate all these quantities: open circuit potential, light harvesting efficiency, driving force, reduction potential, percent efficiency of the die. We did calculate this for the dies we did, and this is the number. So we can provide for the experimentalist a first-hand account, what to prepare and what to skip. At least like the drug design. Like a drug design, instead of preparing all dies and test it, you can, from this calculation, know which die is okay and which die you don't care about. This is the last paper we published. It is just appeared in Journal Structural Chemistry about this unsymmetric squalene die. We want to examine very basic idea, and this very basic idea is the proton-coupled electron transfer reaction. What happens is when the uncoiling group approaches surface, two processes takes place. First of all, a proton transfer. The proton of the carboxylic group is transferred, and now the carboxylate uncoils to the surface. This is a step. This is one process. Second process is the injection of the electron. The question is, which is first? The protonation, the proton loss, the proton transfer, or the injection, or both is simultaneous? That's what we did and tried to answer. And Dr. Absalam was one of the persons who are heavily involved in this calculation in King Abdulaziz University, of course. And we came up with a lot of calculation and said, fine, this is the density of states of these dyes. For the donor alone, for the uncoiling and acceptor, we did a lot of work. And finally, we came to the conclusion that it is almost concerted reaction. It is almost concerted, not stepwise reaction. But this will be continued because we will stimulate the surface in itself and then examine the real process on the surface. Now, there is another kind of dyes because the dyes inside solar cells using donor acceptor dyes like the ones I just saw seems to stay at the ceiling of efficiency. It's going between 10 to 14% efficiency in converting light into electricity. We want more. We want efficiency, higher efficiency. A new idea came that bring an acceptor molecule, complete individual molecule as acceptor, another molecule which is is very strong donor, mix them in a polymer and then allow them to interact. If they cannot be in the same dye, then bring them together in situation. We actually started to calculate this one. This calculation on the indene C6 compound, this is extremely published in this paper. They showed that it is extremely very powerful acceptor. So we started to do a calculation on an indene carbon 60, diindene, and triindene. And we want to establish these as very good acceptors in this situation, and we will select donors because donors in organic chemistry is very easy, and we'll start polymer work on it. So we'll do in the next step, simulate the platinum oxide surface and the dye on the surface, because the behavior on the dye alone may be quite different from when it is absorbed on the surface. This is preliminary results, but looks beautiful. Okay, thank you.
questions? Go ahead.
Thank you. Refaat, one question about this last problem of titanium oxide. Which kind of metal used to simulate this surface? That to be a blend wave, that to be with a periodic structure? Because with TDFT we tried some time ago and it didn't work well.
Yes, of course, blend wave, and we use VASP for this kind of calculation. Yes.
But then, can you simulate an electronic structure of the titanium oxide to make the injection of the charge?
We don't know yet, but we simulated already the titanium oxide. We will allow Absalam to explain this more. He simulated titanium oxide, 5 layers of titanium oxide, and he was able to optimize the dye on the titanium oxide. But this is as far as we went now. We will examine the injection process after. If you want to add something, Dr. Absalam, you want to add something?
We did not start yet working on the TDFT. We just see the film.
We optimize the thing, but we didn't examine the injection process yet.
Okay, thank you.
Regarding business, biotechnology is very attractive. So is it possible to extract chlorophyll from plant and apply it as a photosynthesizer on titanium dioxide?
In principle, any dye can be used as a photosynthesizer. The units what you need your dye to be able to inject the electron into the titanium oxide semiconductor to get it to the metal, to the external metal. To do this, you need some properties of the dye. The excitation, the HOMO is far down, but the LOMO, you need the LOMO above the conduction band of the far higher than the conduction band of the semiconductor, but not very high.
Natural compounds are maybe very available.
Yes, of course, it is available and can be used. I think somebody used it. There is some other kind of dyes, which is metal-based dyes. Metal-based dyes are well known, but it is more expensive and it is not very flexible. So the process is in the market now. Everybody is trying to add and understand things.
Okay.
Thank you. Thank you for your impressive presentation, Professor Refaat. I have just a question regarding if you have tried the perovskite, organic perovskites as a solar.
Yeah. No, we didn't try.
Yeah.
We are so involved in this, but yes, we need to examine it.
It's more complicated
Yes.
for such kind of
Yeah, but
oxides or composites.
unfortunately, we didn't.
Okay, thank you very much.
Any more questions?